All right, so we are going to do question 3.5 on Silverstein 8th edition. So the first data set spectrum that we have is the mass spectrum. So in the mass spectrum, the textbook says that it is using electronic ionization mass spectrum unless otherwise mentioned. So in some of the questions, you will see this CI text next to the mass spectrum. That means it is using the chemical ionization, which is a soft ionization technique. All right. So in this case, it's the electronic ionization, and usually in electronic ionization, the maximum mass, the maximum peak, the peak at the highest end, which signifies the molecular ion, is actually the M plus ion, right? It could also be the M plus one plus ion as well, right? So it could be either. However, we will not be too sure. In general, we'll say it's 168, right? We'll also take note of the other peaks, right? So there's a peak at 153, which is 15, right? I mean, if you consider the difference between 163, 168 and 153, that is 15, right? So I'm going to write it 18, 153 plus 15. So that 15 might be a CH3 group, right? CH3 radical that was removed, right? Maybe, right? Maybe, okay. Siviramana 151. There is a what do you say? It's plus 17, right? So that maybe an OH radical that got removed. OH minus maybe, right? There's 125 plus 43. I don't know what this is. 143 is a particular peak. If you look at the mass spectrum note, you'll be able to notice something in that value range. And plus 60, I'm going to stop it there, right? Then you have the IR peaks, right? Um, the IR peaks, you have a peak at 1705, right? So that may be a carbon oxygen double bond. Now that doesn't mean it's a carbonene, it could be a carboxylic acid derivative as well. It's just a carbon oxygen double bond. There are a bunch of other peaks in the 3000 to 2000 range, right? The bunch of other peaks, and I'll scroll up here a little bit to bring up the IR into view. So as you can see, there's a very broad peak there, which maybe means there's a NH or an OH bond, and the other peaks, at about 2962, and those maybe CH bonds, right? Various CH bonds, maybe. That may be the case, right? So we are going to leave it there. But as a general practice, I'm going to write the peak values, right? So it's 200, 2893, and then 2669. This is the IR peaks. All right, so there's another piece of information that I extract from the mass spectrometer, that is mass spectrum. That is, if you divide 168 by 14. Why 14? 14 is the mass of CH2, right? I get 168 divided by 14, we get exactly 12, right? So that is a coincidence. We don't always get an exact number. So what this means is there are 12 12 say moieties, so units, or 12 12 CH2 mass equivalents, right? Now what that means is we might have a 10 carbon chain plus 2 oxygens, right? Or we could have a 11 carbon chain plus 1 oxygen. Likewise, it helps me get an idea of what probably might be the length of our chain, or 11 carbon structure. It gives an idea on what might be the number of carbons, and it helps as we go along, right? Then let's get on to the um, HNMR spectrum, right? So HNMR, I've extracted the data on my piece of paper, but we'll also go about it in this way. So as you can see, there is the HNMR. So this is how I put the data on my table. So this is the one HNMR, and you have the 1.3 peak, which is, if you look at the height of the integral, it's the tallest integral, right? At the same time, these, I hope the cursor is visible, probably not. Okay, so if you consider these peaks, right, these are 1/3 the height of that, right? If you draw a line like this, you can see it's about 1/3 or half. Is it half? No, it's not that. 0.35, right? So 0.65, you have another line there, which is again thrice the height, right? You can see that this is 1/3 of the height, and this is the probably we can consider this as the other third, right? I'll erase that and try to draw it properly. Point is, it is thrice as tall as the shortest one, right? As you can see. Okay, so I'm going to say the signal corresponds to 3x protons, right? The reason why I say x is x could be 1 or x could be 2, right? If you have a very perfectly symmetric molecule, x might be 2, right? We don't know that yet. We absolutely have no idea about the molecular structure, any such thing. So we don't know. So we're gonna just say 3x, right? We can conclude, and it's a singlet. So there, 3x singlet. That's 1.65. I will draw this in a different color so that it's easy to see. 1.35 is a 3x singlet. 1.65. These numbers, you just have to approximate them by looking at the graph. 1.7, I'm going to call it 1.70 for no particular reason. I mean, it looks like 1.7 on the graph. That's why, right? When you look at the 1.7 graph, the 1.7 peak. Let me scroll up a little bit more. All right, so this is your 1.7 peak, right? Somewhere over there, this little noisy thing over there. So we also have a bunch of extra detailed graphs over there. So this point is about 1030, right? So also it says 600. So we are going to divide 1300 and sorry 1030 by 600, right? So that is going to tell us the chemical shift that corresponds to that point. So 1030 divided by 600 is 1.0, right? So it's, so this particular set that the line, vertical line that I drew corresponds to the 1.7. What do you say? The 1.7 peak. So it's a doublet, right? It's clearly a doublet. So we just put the doublet over there, right? So then we have another one at 1.8, right? 1.8, which is a 2.6. That's and it's also important to notice that the peak at 1.7 is x height, and 1.8 is also only 1x. It's 1/3 of the tallest peak. Whereas it's also, as you can see, it looks like a doublet of a doublet, right? You can also call it also maybe a quadrat, but we can't be too sure. It's not very symmetrical or neat to look at. So I'm gonna call it a it looks like a quadrant, right? So we just say it's a quadrant, or maybe it's a doublet of doublet. We don't know that. I mean, I don't know that at this point in time. The next one is the 1.9. As you can see, there's only one integral that goes over the 1.9 range. There's only one integral that goes over this entire range, right? And that one integral, so it spreads over two signals, as you can see, this one and this one, right? And so we'll have to figure out how much each of those different signal, how the relative heights of the proton density, let's say, that corresponds to those different signals. So there's one at 1.9 and the other one we're going to say 2.10, right? So these are approximate numbers, and so if you look at it, the integral seems to indicate x for 2.10 and then 2x for 1.90, as we can see, because let me take it again. So if you consider this line, from this line upwards, it stops at 1x height, right? So the remaining 2x height must be corresponding to 1.9. So we have another peak at 2.5, which also corresponds to 1x. Oh, we forgot to mention the multiplicities of these things. So again, here you can see it's about 1200, is it? 1180, let's say. Let's we do the same math. So you could just maybe assume what each of those peaks mean. I mean, you could assume, you can just connect these peaks with this ones by just assumption. But it's always better to do the calculation and then be sure that you're connecting it properly. Because if you don't connect it properly, you're definitely gonna get it wrong. Alright, so it's 1180. Here the 600, and that comes around at 1.9. So that peak corresponds to that. And it's a very messy peak, right? So I'm gonna call it a multiplet and also mention it's messy, right? And then at 2.1, you have a very nice doublet, very strong doublet. And you can also infer the J coupling value by looking at the gap between those two peaks. It looks about J equals 10, right? J is about 10. Then you have 2.5, which again, right? 2.5. So there's another peak at about 2.5. And then if you look at this one, right? So we'll do the same math again. How much is that? About 1450, right? So that should, you can see by just let's do the math. It doesn't hurt for us to run the calculation. No, it's 2.41 ish, right? So we can be sure. Sorry, that's 1500 something, no? 1500 something. So that's about 2.5. So we know that peak that I have circled corresponds to the this peak, right? So we are gonna mark that as a doublet because it's again a very clean and neat doublet, and you can see that the J coupling is about 10, right? And then there's another peak at 2.6, a very gorgeous triplet. Again, the height is X, uh, elegantly a triplet, right? And then at the end of the spectrum, you see two singlets, 4.5, 4.6 ish, and then 4.9 ish. You have two singlets. They both correspond to single one third of the tallest peak, and uh, they both looks like singlets. But if you really get close, you can see that they're both. One of them is a doublet, right? This might be a doublet, but this one is for sure a doublet, right? There's some anomaly in the shape of the peak here and there as well. Maybe there are two different peaks on top of each other. We just don't know at this point. So we're gonna, in our data sheet, what we are going to do is we are going to mark it as a doublet, and we're gonna mark this as a singlet and this one as a doublet, right? All right. So to make life easy, I'm gonna mark this using some horizontal lines so that I can easily identify what is what. I don't have a ruler, so it's going to be easy to work with this. And we have it nicely separated like a table. All right, there you go. So we'll add the COSY observations over there. Okay. All right, so let's move on to the COSY observations. COSY was, oh, sorry. That's the C13 depth as well. So we'll go with the C13 depth and then come back to the COSY. So there's some useful information again that we can, apart from what the C13 tells us right away, that we can extract 13C depth. All right. So let's look at the graph, right? So, oh, I missed one signal at the bottom here. In the HMR, there was a signal at 12. This is a very characteristic peak. That probably means that you have a carboxylic, right? And the nice thing is that so far, that's not 12.0. We can maybe 11.9, right? So it's one proton height, the integral, and then it's a broad peak. And that is probably the OH proton of the carboxylic group. Okay, that's usually you see a broad peak and this far upfield. That's probably a carboxylic peak. So we have the C13 depth here. For that one, right, we look at the table. You could see the first one is at about 19. The height of the peak gives us no useful information. The depth clearly tells it's a CH2. 23 is also a CH3. I'm just going to write these things down right away. 28 tells us it's a CH3. 29, the depth is telling us it's a CH2. The depth is very convenient, to be honest. You don't have to think much once you have the depth with you, because it tells everything right away, right? 39, and then signal at 439 is a CH2. 41 is a quaternary carbon. 52 is a CH. All right. 110 is a CH2. And then 145 is also a quaternary carbon. And then finally 180 is again a quaternary carbon. So everything about the data that we have right now is telling that we almost definitely have a carboxylic acid. I'm going to do something else. I'm going to consider the mass of these units. This is 14 atomic mass units. This one's 15, this one's 15, this one's 14, this one's 14, this one's 12 because carbon and no hydrogens, carbon and one hydrogen 13, carbon and two hydrogens 14, just the carbon is 12, just the carbon is 12. You consider the total of that, it comes up to 135, right? So at 135, if you consider the difference between 168 and 135, right, you have 33. All right, so 33 is the mass of two oxygens plus one hydrogen, right? So that means the depth doesn't account. I mean, if you're looking at the depth, then it doesn't capture obviously the two hydrogens and one oxygen. Again, that is an indication that we have carboxylic acid. And then look at the number of protons you have. How many protons? 2, 5, 10, 15, 15 protons, right? So here you have 3 plus 3 is 6, and then 10, 10 plus 16. There are 16 protons in this one. I mean 16 x's, right? If you add it, there's 16x. Yeah. If this one doesn't obviously capture the carboxylic acid's acidic proton, you don't see that come up in the C13 depth when you add the number of H's that turn up here. So we can say at this point that x is equal to 1, right? X is equal to 1. We can be sure about it. There's also something else that we can be sure about. It's the molecular formula, right? You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have C10, all right? C10, H16O2, right? So if you do the calculation for this, which is 12 into 10 plus 16 plus 2 into 16, right? That gives us 168, right? So um, that's another reason why we can be sure. Let's double check to be on the safe side. 2 into 168, right? So we know that this is a molecular formula, right? Now there's another very useful information that we can extract from this as usual. 10 into 2 plus 2 minus 16 divided by 2, right? We understand that there are 3 unsaturations. Uh, that's an important observation, right? So if you have a carboxylic acid, right, and then now we'll look at what we have here. Let me, before we go to the correlation graphs, let's try to interpret what we have here, right? You can see that there is a 110, 145. You see this um, C13 shifts, right? So that means that there's an olefin. These olefinic protons, and this is probably a terminal olefin. Sorry, olefinic carbons. These are olefinic carbons, and then this is probably a terminal olefin over there. So that accounts for one of the unsaturations. So it's a double bond, right? One of the unsaturations is a carbon-carbon double bond. The other unsaturation is a carbon-oxygen double bond. So when you look at this data, you don't see another, because these two probably make up the carbon-carbon double bond, right? These two. This is your carboxylic proton, sorry, carboxylic carbon. The other ones, none of them can have an unsaturation. So that means our compound is cyclic. As a cycle syndrome. Okay. All right. So let's move on with the remainder of the. We look at the correlation data, right? And then try to interpret that. So this correlation data is in this particular graph is a little disorienting because there are so many peaks, right? Because if you consider, write this in blue color, 1.33x, right? It's a singlet. But if you look at it, it correlates with a bunch of different points. There's an issue there. So we are going to ignore it, but we'll write it down nevertheless. Right? 1.35. You can see that there is a COSY correlation at these points, right? You consider this graph, right? This line correlates at 2.5ish, and then correlates at this point as well, about 2.65 or 2.7ish, right? So similar way, if you extract the data, you could maybe draw these points, like 1.9 correlates at 4.6, and there are so many points for what should be a singlet. That's very disorienting, to be honest. 6 and then 1.2. So 1.71 indicates peaks at 2.6, right? 2.1 and then 1.9 and then 1.8, right? So similar way you can get this data written down. 1.8 has peaks. 1.8 is less confusing. There are 2.6 peaks and 1.9 peaks. 1.9 correlation, there's a correlation 0.8, 1.7, and then 1.6. All right. So next one again at 1.9, there is a correlation with 2.6. There's a correlation with 1.9ish. So we might not be very accurate with these numbers because we are just looking at and then putting it on our table. 0.8, 1.7, 1.6. If you consider the 2.1, you have correlation with, there's another important thing, right? The J coupling is same, so we can right away guess that these two are probably correlated with each other, and that is confirmed by what we are seeing over here in the course. And there's a 1.3 correlation, which is again the disorienting correlation that I talked about, and then the 2.1 correlation. The 2.61 is correlating with a bunch of stuff, correlating with 1.6, 1.7, 1.9, 4.7, 4.9, and then 4.6 as well. 4.6 and 4.9, if we look at them and see if these are correlated. Yes, they are very much correlated. So this, and then this one is this. So the 4.6 is correlated with 1.65. Again, these are very confusing, right? It's not supposed to be doing this because 1.65 is a singlet. 4.9, and then finally, this is again correlated to 1.65, 2.6, and 4.6. So this is these are our COSY correlations. So I mean, we'll keep this before we go anywhere, right? This just can't be right. It's a singlet, so we're going to ignore this. We are going to ignore the ones that I'm going to mark with a black dot. So this is ignored. Ignored. The 1.6 everywhere they have the 1.3. We're going to ignore it. Okay. 1.6, we are going to ignore these things, right? Because that's disorienting, right? You can't have a CH3 singlet having these many correlations. Yeah, so these are going to get ignored, right? We're going to work with the remaining ones because sometimes like COSY spectrums can give noises, so unexpected observations, which we should know what to ignore and what to keep in mind. Let's move on to the HMBC correlation. So there is no correlation for the proton at 11.9, once again confirming us that it's the carboxylic peak. So this is the HMBC correlation, HMQC correlation, which is one bond, right? HMQC is one bond or two bonds? Okay, so HMQC is going to tell us one bond correlations, which is what we have here. Okay, so again, I'm not going to be looking at the graph again because I looked at it once. Just going to write it down here. This is 1.7, 1.9, right? As expected, CH2, two signals to 1x. I mean, these are corresponding to a single carbon, right? Single proton, and you see it confirmed right here. 4.6 and 4.9. Sorry, oh, these are HM. Okay, so what I'm writing here is going to be the HMQC signals. And there's a separate HMBC as well at the bottom towards the lower end. So this is HMQC, which is going to be the single bond correlations, right? So it's 1.8, 1.9. Okay, 1.65 is a 3x correlation. 1.3 has 3 carbons and again 3 protons, and it agrees with CH3. 1.7 and 1.9. Okay, so this is interesting. You can see that 1.9, 1.9. So 1.9 is actually 2 protons, right? But they are coincidentally, they're not 2 protons that are chemical shift equivalent. They are chemical shift non-equivalent protons that are coincidentally having the same shift. That is why you get a very messy peak multiplet over there, because these two are overlapping. And then you have for proton 39, you have 2.1 and 2.5, which is not shocking because those two are very closely correlated. So this one doesn't have, obviously. And then this one has the proton at 2.6, which is a single proton, and it agrees with what we are seeing, right? Here you have a 4.9, 4.6 proton. So with this, we can just be confirmed that this is a terminal olefin and live with that, right? Similar way, you could extract the HMBC data as well. I'll try to put that on the screen as because there's no space here to write. The HMBC is critically important in starting to elucidate the structure, right? For HMBC that I have is 1.7, 1.9 for the first proton, 4.6, 4.9 on the second proton, 1.7 second carbon, 1.7, 1.5. If you look at the signal, it looks like a two bonds. It's a very intense signal, but you can't be too sure, right? It's 2-1. For the carbon at 29, you have correlations, HMBC correlations at 1.3, 1.8, 2.1, 1.9, and 2.5. So 39 has correlations at 1.3, 1.7, and 1.9. 41 has correlations. There are so many correlations for 41, right? Which is not shocking because it's a quaternary carbon, so it must have many correlations in HMBC, right? 1.3 is HMBC. That is 1.3, 1.6, 1.8. There's a correlation with the signal on 1.9, 2.1, and then 2.5, 4.6, and then 4.9 as well. Right. The 110 signal correlates with 2.6 and 1.65. The final signal at 145 that correlates. Okay, I got a little confused with the way I have written it, right? 1.4, 2. Okay, I'll have to erase this a little bit. How did I erase my eraser? Okay. I got a little confused over there. The way I have written it isn't very clear in my paper. 1.3, 1.6, 1.7. This is 1.7 over there. 1.9, 2.1. There's 1.8 also. Maybe 2.5 and 2.6. Easy correlations. Pretty much the same set over there, right? You have 1.3, 1.6, 1.3, 1.6. There's a bunch there, right? So I'm gonna leave it 1 for 2.6 and then 1.65 for the 110 signal. Then for the 145 signal, so finally there is a bunch of other protons that come at the bottom of the list. Probably 110, 145. So these are 2.6, 1.9, 1.8, 1.65, 4.6, 1.5. And these guys correlate only with 2.1 and 2.5. Right? If you look at the HMBC, it's a very neat correlation for this one, right? These two only very clearly correlate. Our native power only very clearly correlates with 1.5 or 2.1 and then 2.5. So with this data, I have it in a paper as well, right? So we are going to try and solve go for the solution of this using the data that we have here right now. So I'm trying to not to erase what we've written from here, right? So let us move this a little bit so that okay, everything is visible. All right. Okay, so I'm going to erase the mass data. We will come back to it later. I think we've extracted most of the data that we can from the mass. We can focus on these, right? So I'm going to erase all of that and then we can start drawing the structure. Okay, okay. Try to get closer a little bit so that see things more clearly. Okay, okay. So we know that there's a terminal olefin there, right? So we'll start with that. Start with the terminal olefin. Carbon-carbon double bond. It's telling us the proved protons are 4.6 and 4.9, right? Those are the two proton values. There's a carbon over there. There is a hydrogen over here, right? So, so the HMQC is also telling that the shift for, okay, sorry, there is no hydrogen over there, right? There's only two carbons. So there are two carbons here. We don't know anything about it, right? But if you consider the this correlation, right? Because this is your 145 carbon. The terminal olefin is this one, right? This is your 110 carbon, right? And this is your 145 carbon, right? Okay. I hope it's visible enough. Move a little bit closer. Okay. Okay. All right. So 110, 145. Where are we now? So now that we have it aside, we'll look at the HMBC, right, and then try to guess at what might be the structure. So the 145 correlates with 2.6, 1.9, 1.8, 1.65, 4.6, and 4.5. So 4.6 and 4.9, that is agreed, right? So there's the 1.2.6, 1.9, and 1.67. So the 1.65, sorry, 1.65 is this, right? It's a CH3 carbon. So it could be 1 to 1 to 1, 2, 3, right? If this is a CH3 over here, right? So we are going to just put it and then see what happens, right? So this is your 1.6 proton, if that's the case. I'm going to put it there because it's in a corner, right? The terminal. So 1.6 over there, we'll erase this, right? And then at the next carbon here, right? So if you look at the other carbon, there's 1.9, 1.8, and 2.6, right? So let's look at the 1.9 signal. That there are two 1.9 signals, right? That is hard for us to come to a decision on. There's also the 1.8 signal, which is one proton, and you can see the 1.8 and 1.9 down on the same carbon. So this 1.8, 1.9 is this 19 carbon is somewhere close to this, right? So it could be this one, it could be this one, right? The carbon 19 could be this one, maybe, right? It's not, we can't dismiss this possibility. It exists, right? Right, and then 2.6 is 2.6 corresponds to this one, right? So it's a CH, it's a single CH, so it has three bonds like this, right? So like we earlier also noted that it's a cyclic carbon, cyclic structure that we have. So this is the possibility that we have, right? Sorry, there are two bonds. So maybe the cycle, it joins the cycle at this point, right? Maybe, okay. So if this is one possibility, maybe these two are struck as well, because 1, 2, 3, right? It could be either ways. We just don't know what it is, right? So let's look at this one. These two signals, right? If you take the record, right? These two 1.3, 1.6, 3, 1.6. 1.3 is this one, 1.6 is this one. So this one is pretty close to that one, right? This 52 signal is quite close to the carbon 19. It has to be at least 2 bonds, right? Whereas this one does not have any indication about the all of these protons at 1.6 or 1.3, right? So if it were carbon 19 was here, if it was here, right, this would give a HMBC correlation 1, 2, 3, right, with the 1.6 proton. But we don't see that, right? Carbon 19 does not give an HMBC correlation with the 1.6. So that means probably it's not like this. Rather, we have it like this. CH, all right. So you have your 2.6 proton over there, and then you have two protons. One of them is carbon that corresponds to 19. This one corresponds to 52. That's a very upfield carbon, which is interesting. We'll think about it later, right? And this one would be 23 at this stage, right? Maybe it is wrong, maybe it is right, we don't know. So there are two hydrogens on this one. One is 1.7, the other one is 1.8, and then 1.9, right? Okay, so that, right, 1.8 and 1.9. As you can see, now there could be made a counter argument. If this protons, why do we not see a HMBC correlation with 2.6? I don't know, right? At this stage, I actually don't know. Right? So maybe we could visit the HMBC for a second and then see if it does have any sort of interesting information. HMBC, we are trying to figure out the 19 carbon at 19, the shortest carbon. You see, there's a bit of a something over there that indicates that's an indication that maybe we've got it right. Right. So this question of whether our decision to, I hope you got what I'm trying to say, right? If this carbon, if carbon 19 is here, it should show a correlation with this 2.6, 1.2 bond correlation. But we don't see, right? In the list that I put. But if you look at the HMBC, there's a very small signal which I earlier ignored, thinking that it's probably a noise. But maybe it's not, right? Okay, so we can see that 1.8 carbon 19 to HMBC correlation with 1.7 and 1.9. Right, so 1.7 and 1.9 is in another carbon, this carbon at 29. So we are going to draw this like that, right? Carbon at 29, 1.7 and 1.9. Okay, so look at this as well. Correlates with 2.6 as expected, right? This one correlates with 2.6, 1.9 correlates with 2.6, 1.7 correlates with 2.6. That's too much. But as we ignored the 1.6 signal in the earlier case, maybe this is an unexpected signal that we're seeing, right? Maybe not. All right, so that's it in this side. So we'll mark the carbon as 1.7 and 1.8 was in, this is carbon 29. Okay, so we have placed 1, 2, 3, 4, 5, 6 carbons. There are only 4 more carbons to place. Okay, so we'll also, so what about carbon? It correlates with 1.3, 1.8, 2.1, 1.9 and 2.5. If you take the 29 carbon in the if you look at the C13 data and the HMBC correlation, it correlates with 1.8 and 1.9 as expected. It's these two protons, and then it correlates with 2.5 and 2.1, right? So we don't see the 2.5 and 2.1 here. So maybe it's right next to it. Right? So when you say maybe the carbon that has 2.1 and 2.5 is right next to it, There's a very important observation or important thing for us to think about. Um, right? Maybe, right? So this is a maybe, yeah. 2 point, sorry, 2.5, 2.1 in this carbon, and then what is it corresponding to? Carbon 39, carbon at 39. Okay, so we leave it there. Because we have another important clue here, is this carboxylic structure. Right? The carboxylic structure, if you consider the COOH, this carbon only correlates with 2.5 and 2.1. Okay, so if it's a 2 bond, okay, so 3 bond, right? If you consider the 3 bond correlation, 1, 2, 3 bond correlation, right? What we are understanding here is that uh, if you look at the 3 bond correlation, all right. So we were talking about this particular carbon, right? So it could be this, and then there is a quaternary carbon over here. So 1, 2, 1, 2, 3. There are no protons here, so it doesn't show any HMBC correlations, right? That's one possibility. There is an alternate possibility, right? Because we have to be open to the fact that anything is possible, and then we have to reject the impossibilities. And the alternate possibility is you could have a carboxylic like this, right? And then you have a carbon, which is a quaternary carbon, right? And then one of these has 2 protons, which is the 2.5 and then 2.1 proton. The problem with this model is you already have one quaternary carbon here, right? So for this sort of setup to work, these also have to be quaternary carbons. That means there should be 4 quaternary carbons in our molecule for it to work, but our DEPT clearly tells us there's only 3 quaternary carbons. So this arrangement is not correct. What is correct is this arrangement, right? What is correct is the arrangement that I drew earlier, where you have this sort of setup, right? So this is the 2.1 and this is the 2.5 protons, and then you have a quaternary carbon over there, right? So this is what is probably possible. Okay. So let's develop this one and then try to figure out what sort of idea we can get. So this quaternary carbon has to be this, right? 41. It correlates with 2.1 and 2.5, so that kind of makes sense. HMBC correlations are there. There are 1.3 and 1.6 HMBC correlations, which is interesting. We'll have it in mind, right? There's 1.7 and 1.8 as well. So, and it also correlates with 2.6. So this proton has to be somewhere close to this, right? So there are definitely 3 carbons here, right? There are 3 carbons here. We've already placed 1.6 proton over there. This proton 1.6 CH3 is already placed over there, right? 1, 2. Okay, there's a line over there. Okay. This proton is already placed over there. Okay, so that's there for sure, because if you consider this 110 proton, it correlates HMBC in one with the 1.6 proton. It has to be there, right? Same with the 145. The carbon at 145 correlates with the 1.6 proton as well as the other bunch of protons. So it has to be there. It has to be there. Also, you can also see that the 145 carbon 145 correlates with 2.6, which is this one. HMBC correlates with this one, with this one and this one, right? So the 2 protons on this side of the carbon, because 1, 2, 3, right? 1, 2, 3, 1, 2, 1, 2, right? 1, 6. It also correlates with 4.6, 4.7, but it doesn't correlate with anything apart from these protons, right? So probably you have a quaternary carbon over there, probably. And since we only have 3 quaternary carbons in our system, which is the carbonyl, which is the C double bond O, and then this particular carbon. These both are probably the same carbon as well. All right. Okay. So in that case, this probably has the 2.6 proton, which adds up because now we has this one has to be the 41 carbon, right? So it correlates with the 2.6 HMBC, right? HMBC correlations are there. It correlates with 2.1, 2.5, 2.6, and then from this 2.6 right over, if this is your 41 proton, if this is your carbon at 41, right? Then it 1, 2, 3, 1, 2, 3. So 1.9, 1.8 both correlates, right? This is probably wrong, right? Because it's on the other side. So this is wrong. Okay, that was wrong. Okay, so probably it also correlates with 1.7 and 1.8 as well, right? So the HMBC correlation 7 and 1.8 as well. So it is this and this. It also shows HMBC correlations with 1.9 and 1.7. So it can't, if 1, 2, 3, 4, right? That's not usual for HMBC correlation. So most probably there is a bond like this, right? There's a bond like this, which explains the correlation with 1.7 and 1.9 HMBC correlations. Here you have the CH2, this particular part that we drew, and then the CWH, right? So this is 2.1, 2.5, right? Uh, that's probably the arrangement. So we are also left with HMBC correlation from this one with the 1.3 carbon. Maybe the CH3 is over there. All right. So this is going to be the 1.3 carbon. Okay. So this is as expected a singlet because there isn't any 1, 2, 3 carbon correlations to give anything other than singlet. This one also same. There is no 1, 2, the second carbon. There's no proton. It's next to a counter carbon. So as expected, these two are singlets, right? But it's close enough. If you look at this, right, the 1.35. Okay, this is, we'll have to discard that as noise. Yeah, so when you consider everything, that is probably our structure. We'll try to draw this in a more neat way. So I'm going to erase everything and then draw it in a way that is more neat. Okay, before we do that, I'll name all of the carbons and the protons in this messy structure itself, and then we'll go to the neat structure so that we can have some kind of connection. So this is your 11.9 proton. Okay, so we are going to mark everything and then get this done once and for all. So this is 180. Proton is marked. This proton 2.15, that is proton number 39. Sorry, carbon at 39. And this is, we have the right number of carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. One carbon appears to be missing, is it? That's it. 1, 2, 3. There are 4 carbons in the loop, and then that's 4, 3, 7, and then 3 over there, that's 10. 10 is okay, so we have all 10. This is 15, right? I think that we've marked everything, right? Yeah. So I'll draw this in a very nicer and proper way, and we'll be done with the solution to this problem. So I'm going to erase this whole thing and then draw it. Okay. Yeah. Okay. All right. Okay, so the problem that we are having, so we can see there's a 4 carbon ring over there, 4 carbon ring. We will draw it very nicely so that we can name it very nicely. So these two have hydrogens only, right? This one also has one proton, and then there is a olefinic carbon, which is a terminal olefin. Has different chemical shifts because it's not symmetric about the point. This one has 2 carbons, right? And then this one has 2 protons, and then finally the carboxylic group. So the numbers are going to be, we'll mark this one's in red. So you have 180, 39, 23, 145, 110, and one is 52. This one is 41, this one is 29, and this one is 19. This CH3 is look at my correlations table. 1.3 is correlated to 28. This is 28, 23, this is 29. Carbon at 19 is correlated to these. So, all right. We'll mark the protons. The protons are, this one is the 11.9 proton is this one. I will mark it in green because it's a very distinct color. 11.9. This one is 4.6 and 4.9. Okay, so there's a question on what is 4.6 and what is 4.9. 4.9 is a doublet, right? So the question is which one is going to have the most. I mean, 4.9 was a more obvious doublet compared to 4.6. So because trans coupling is more stronger than cis coupling, we're going to mark this as 4.9 because it can couple with this one to form a doublet, right? That is the argument that I'm going to work off of. Whereas this one, if this coupling was strong, then that would have led to a quartet, right? But if you look at the signal, if you look at the signal, the HNMR signal, which we are going to do now, we can see that the 4.9 kind of like a quartet. This is more like a singlet, right? 4.9 is kind of like a quartet. This is the more stronger correlation. We have to change that. Okay. Right, so this is 4.9 and this is 4.6. All right. And then what else do we have? This is 2.6. This is 1.9 and 1.8. This is 1.7 and 1.9. This is 1.3 and this one is 2.1, 2.5. So that's it, and this one is 1.6. So there you go, the structure that I elucidated from the question 8.35 in 8th edition of Silverstein. So the workflow that I used, I could describe it like this. I'm going to erase this structure that I earlier drew. Could describe the workflow that I use in general. So for the mass, right, and you get the total mass plus the number of CH2 equivalents, right? And then you go to the IR, take a guess at the functional groups, right? and then we go to the 1 HMMR, and then we get the number of you get the arrangement of protons and all of that, right? And then you plot, you sort of list down the 13C depth, right? And then from this you get the mass contributed, right, by the hydrocarbon structure, right? So by the hydrocarbon structure, right? Using this and then this, you can get the molecular formula, molecular, or rather the empirical formula can be guessed using the observations so far. Right, from there you can simply carry on using the correlations and then finalizing a solution. This is the workflow that I usually use, and I wouldn't say it's fast, but it works. Yep, so that's it.